Thanks for coming. Can you hear me all right? Is it not too loud? OK, good. I actually started tinkering with the this OSV project that I'm going to talk about about 3 years ago. And I used to give this presentation from time to time, but beginning of this year, something happened. So basically, a good friend of mine, Brian Cantrill, reacted this way to the purchase of the microkernel, Unikernel group by Docker company. And his idea was that the unikernels, which OSV is an example of, is an absolutely bad idea. He even wrote this blog post that I actually highly recommend to everyone because it actually touches upon some really interesting issues in how and what unikernels are trying to do with the application deployment in the cloud. But I think the frame of reference that Brian is coming to is slightly different from, maybe actually a lot different, to the frame of reference that I will be trying to pursue in my presentation. Because to him, the application deployment in the cloud is basically old school. It's kind of like how we used to build applications, where developers were really aware of the underlying operating system. And what I will be talking about is something that happened only recently. So my frame of reference is basically platform as a service. And I will be using one of the examples. There's a few available. Cloud Foundry is a good one because it's pretty widely adopted by the industry. I work at Pivotal, so obviously I have to give at least a couple of slides to Cloud Foundry. But in general, Cloud Foundry basically gives you a really different model of how developers interact with the underlying platform. And like I said, different companies are investing. And most of the companies on this slide are not just in the companies supporting Cloud Foundry organization, but they're actually practitioners of Cloud Foundry. So they have internal development teams essentially using the platform to basically develop and deploy applications day in and day out. So how do they do this? No, seriously, how do they do this? So basically, the application is sliced into chunks that then gets pushed into the platform. That's it, done. Like there are no containers, there are no Docker files, there is nothing. It's very similar, conceptually to how J2EE application developer would interact with the application server, where all you have to know as a developer is that you have to produce a WAR file, and the rest you don't even know about. Like whether your application server is deployed on Unix or Windows or maybe AIX, you have no idea, and you don't need to worry about any of that. So Cloud Foundry is the same, similar approach, and it works extremely well. But it works extremely well for a certain class of applications. If you have your traditional J2EE type of application, you actually a little bit out of luck. You kind of have to refactor and re-engineer your application to be following these principles. So those types of applications are known as 12-factor applications. And I won't go through all of the principles, but for those of you interested, 12factor.net gives a really good overview of what it means to be a 12-factor application. Most of this stuff is basically self-explanatory. You basically have to have configuration that is separate from the applications. You have to have port binding that is outside of the application. So you basically have to kind of communicate to the platform how your application needs to behave. But most important of all, your application has to be stateless, which means that your application basically has no identity, or parts of your applications have no identity per se. That identity may be stored someplace else. So your application may talk to the database or some kind of a persistent store outside of the application. But the platform doesn't know anything about what it means to hold a certain state. And what it allows the platform to do, it basically allows the platform to manipulate your applications in all sorts of ways, scaling it up, scaling it down, doing rollouts without worrying about how to persist that state that may be unique to this chunk of application that is being manipulated. So in practice, this looks like this. You typically have oh, man. This looks awesome. Wow. I guess. Huh. Yeah, this is pretty bad. So basically, you have essentially a manifest for your application, which essentially is a YAML file that explains a few things about the application itself. What chunks of the database the application has to interact with, what ports it expects, what configuration variables it expects. The YAML file, typically, again, hopefully maybe we can get at least a glimpse of it, or maybe not. Right. This is not going well. You know what? Let me try something else. Let me quickly try something else. Yeah. Okay. So let me see if maybe I'm pretty sure it's a laptop issue or sort of the issue with the okay, view full screen. This is just okay. Okay, this is actually better in a way. Well, maybe not. This is I haven't seen anything like that. But basically, so this is no, this is annoying. This is now officially yeah. Huh?
Let's switch to some fights.
Nope. Does anybody have a different laptop? Mm-hmm. 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 Yeah, I've got it here.
Oh, no. I didn't do it.
Do you get...
We figured it out, don't worry.
oh, you've got it? Anybody can,
We have a Windows.
Yeah, Windows is fine. I have a PDF here, so. Yes. Nope.
This one got a... Nope.
Ooh. This is.
Which I know we... So this is DisplayPort on this end? Yeah, we just got DVI and... oh, I see. Oh, DisplayPort? Yeah, Mini DisplayPort? No, sorry. Yeah, it's normal.
Man, this is not going as I planned. Okay, so let me try something else again. So if you can try to find a laptop, that would be appreciated. Well, for now, let me. Huh?
Let's do this. Let's transfer this.
Yeah, I've got it already here.
And we'll use this computer. And let's give it a shot. I'm sure it will work out.
So do you have a USB?
Thank you for your patience, all of you. And helping Roman.
Yeah, thank you, guys. Mm-hmm.
Sure, we're going to try all the laptops pretty much.
Yeah.
But we'll make it work.
Yeah, well, we have to display it first. Yeah, first one. Yep.
Make flickering slide. Yeah,
Yep.
this one. Finger toes crossed.
Yeah, no. It's that.
OK, which one?
It's
Yeah, you can.
Oh, yeah.
There's this one.
So on that side, it's mini display ports. Yeah, that's perfect.
OK. So then we need this one, and then this one. Yeah, they have like a really convoluted. Oh no, actually.
I have HDMI on that side. What was it?
Yeah, I haven't I haven't seen this one ever in my life.
Interesting. Yeah.
Yep. So let's OK. Oh, OK. Yeah, that's German. System settings. Systems preferences. Yeah. Yep. Not here. Not yet. Yeah. So monitor. Yeah, and just make it mirror. If only I understood German.
Mirror.
Yeah.
Super. Thank you so much.
It's still flickering, but I think it's better. It's way better than it used to be. So, yeah, can you go full screen? Awesome. Yay! Thank you. Yep. All right, so I will try to talk real fast, because we kind of lost a little bit of time, but the good news is you can actually see it. So this is how the manifest file looks like. And basically what the developer has to do is just this, right? CF push. And then using that manifest file, what the system does is essentially it builds a whole bunch of images. And those images are known as droplets. So those images are essentially the application source code, something that is known as build pack, basically all the sort of prerequisites for that source code. And then a file system stack. It's kind of like kernel and all these bits and pieces that glue everything together. So then, for example, once you deploy your application and you want to scale it to a different number of instances, you can actually do it automatically, but you can do it manually as well. And all that system needs to do is to basically sort of copy those droplets onto different sort of containers, and off you go. So the idea here is that the anatomy of the droplet is basically some of the microservices code. Sort of, again, that's the piece of your application. Some kind of a virtual machine. Most of the time, it's typically Java virtual machine. But if you think about it, Go runtime could also be considered as a virtual machine. Then there is some stuff. And obviously, there has to be hardware for all of it to be executed on. So how are we doing it today with Cloud Foundry? So most of it is basically done through essentially runc images. So we don't actually use, we can run on Docker, but we can also just use runc images. And we kind of put the sort of minimum version of Ubuntu as a base image, and put sort of the build pack and application code on top of that. So a better way, and I think that's what this presentation is about, and again, that's why I think Brian was a little bit off in his comments, is that if we can reduce the amount of the operating system that we put into each of those containers, we win because the image becomes much smaller, and especially on the sort of already virtualized environments like public clouds and some of the OpenStack deployments, we avoid sort of this double virtualization. Sort of we avoid virtual machines, and containers within the virtual machines. So basically, this is the taxonomy of everything that your sort of container platform could support. So this image was done by Graham Dumpleton, and I really like it because basically you have the container image, and there is nothing wrong with it. You can still use it, but the unikernel-based container image is much smaller and thus much easier to manage and scale. And that thing on the right is Java runtime, which is big either way you look at it. So what is a unikernel? So unikernel as a concept was actually around for quite some time, but it got kind of sort of into the public view, I would say, in 2013, when this research paper was published. And the whole notion of a library operating system was introduced. So basically, we all expect our operating system to be, sort of a kernel, and then a whole bunch of user code. So what these guys for the first time proposed is that why don't we put all of the operating system kernel and the application itself in the same sort of image and run everything within the essential ring zero. And of course, there's a few things that we cannot really do. We cannot, for example, have multiple processes, sort of switching because, that's sort of one image running within the, one sort of address space. And this executable, because it really becomes an executable, this executable can only be sort of run on top of some kind of virtualization system. So it's QEMU, VirtualBox, VMware, Xen, public cloud, you name it. So how do we build it? That question was actually answered by Antti Kanti through a different sort of work that he was doing with the NetBSD system. And his work was focused on any kernels. So what he was trying to do with the NetBSD is to basically kind of refactor it into a set of components that can be leveraged in all different contexts, right? Because if you think about it, inside of your kernel implementation, you basically have things like, let's say, TCP/IP stack. Now, that piece of code could actually be useful standalone as it is, and there is absolutely no reason for it not to be able to sort of turn into a library and link, let's say, a custom TCP/IP stack into an application that's running even in user space mode. So what Antti was doing, he was basically refactoring the build of the NetBSD to make NetBSD essentially much more granular and be able to export those useful bits and pieces to other use cases. So that's actually what I see when I talk about him, because in a way, for those of you who are familiar with Futurama, Antti is basically back alley doctor of NetBSD. He kind of like just cut NetBSD into a whole bunch of organs, and you can actually still run NetBSD that way. You can kind of like put it back together, and that would be a sort of an operating system, or you can basically use it in all sorts of different places as well. So unikernels, either way you build it, either through any kernel or a specialized kernel, is basically a couple of implementations that you can get today, and you can start playing with it. So the granddaddy of them all, that's the implementation from which the 2013 paper got sort of published, is a Mirage OS. It is sort of a Xen-based thing that was actually developed by a group of people in Cambridge around sort of OCaml. So everything that you do has to be in OCaml, but if you sort of subscribe to that notion, you actually get a pretty decent amount of optimizations, that you can pull off. So again, a good example would be, so suppose your application doesn't need, let's say, UDP, doesn't need to say, send UDP packets, right? This compiler can analyze, the dependency chain and basically figure out that the kernel doesn't need to have that part of the sort of TCP/IP stack, and just like a static linker wouldn't link an object file that you don't need, it wouldn't actually link, the portion of the TCP/IP stack that deals with UDP. So stuff like that. But again, you have to basically kind of, jump into OCaml, and certain people like it. I don't really have an opinion one way or the other. So and then there is Clive. Again, it's a research project out of University of Madrid. So they're trying to do a unikernel based on a Go operating system. So there is some lineage going back to Plan 9. So it's kind of like the same research group that did Plan B. It's a very nice system because at least it sort of deals with the language that everybody's familiar with, but it's still pretty research in nature. So like I said, rump kernels is sort of Antti Kanti's way of doing sort of unikernels. And then OSV is what we will be talking today about. But before I actually start talking about OSV, because you have this great collection of technology that provides you capabilities of doing unikernels, a way to essentially manage it emerged. And this is the project called Unique. It's basically, think of it as a GCC toolchain for different kind of unikernels. Right? So basically, this project allows you to essentially focus on your application instead of on focusing on sort of the differences between different unikernels and how to run them. So you get a decent sort of command line utility to basically play with all of them at once. Today it supports OSV and rump, but they're actually building a lot of support into Unique, and I actually really like it. for two reasons. First of all, it has a Docker API, so a Docker client can actually manipulate unikernels thinking that it's talking to the Docker daemon. And second of all, this project is actually what we're prototyping as a backend for Cloud Foundry. So that sort of introduction that I've done around how Cloud Foundry scales the applications, Unique is likely to be the implementation that we will prototype it around. So take a look at it. Now, let's focus on OSV, because that's the subject of today's talk, and that's actually, to me, the most interesting of the unikernels out there. So what is OSV? So OSV is a unikernel focusing on POSIX functionality. So the idea behind OSV is that you should be able to take anything that is a POSIX application, completely unmodified, and essentially link it with the library that OSV gives you, and turn the whole image into essentially an application that will be, like I said, running inside of the same address space, in ring 0. But any kind of POSIX system call that you do would still be supported. It runs on top of KVMs and VirtualBox VMware, so basically full gamut. And it's pretty fast, as unikernels go, but it's not as small as something like OCaml. Because again, POSIX is actually a pretty big standard. You have to provide a lot of functionality to be POSIX compliant. So OSV manifesto, very quickly, they have an explicit goal of running existing Linux applications. So the only thing, and I will talk about it a little bit later, the only thing you have to do to an existing Linux application is if you have a build that produces a.out, kind of sort of elf executable, you need to modify that build to start producing shared object, with a special entry point so that the dynamic linker that is running inside of OSV can sort of dynamically load it and start executing it. But that's literally the only change that you have to make. So they're trying to make boot time comparable to the execution time. So basically, their explicit goal is it should take OSV unikernel to boot the application, the same amount of time that it takes the real operating system to actually execute the very same application. And they're trying to stay open. So the group that is doing it was actually the same group that did KVM implementation in Linux. So they used to be really focused on OSV. They're still pretty focused on OSV, but I think they are now shifting their focus. So if you guys are liking what I'm talking about today, jump on the GitHub and help sort of with OSV development, because the focus is shifting a little bit. Again, it's not that the project is being dropped. It's just that we need more sort of volunteers to help OSV go along. So what's inside? So let's just talk about how it's all implemented. So like I said, it's basically an image, right? It's the same image that, let's say, your sort of full virtualization build would produce when you're producing VMDK or any kind of disk image to be basically booted on one of those virtualization solutions. So inside of that image, you basically have C++ kernel code, written from scratch. So that's the difference between sort of an any kernel approach, because in the any kernel approach, that kernel code would be taken from NetBSD. So that's sort of how they do it. In the OSV's case, they wrote the kernel code from scratch. It's C++, C++11. It's actually a pretty clean, sort of nice C++. So again, if you like, C++, that's one of the nicer projects, to get to go at. So then there's basically a dynamic linker that links a whole bunch of shared objects. Remember how I told you that the only sort of change that you have to make to your existing application is to turn it into a shared object? So basically there is a shared object for things like libjvm if you're running a Java application. And then there is a whole bunch of modules that implement typical functionality of the operating system, like being able, for example, to talk to a file system. What's interesting about OSV is that they decided to take a file system from OpenZFS project, actually by the way of NetBSD, but still. So it's a full-fledged ZFS implementation, which again, nowadays that Ubuntu is shipping ZFS, it's not sort of that super cool. But it used to be that you can actually do a lot of cool things with ZFS, like snapshot rollbacks, sort of within this unikernel approach, which again, to me, is really, really cool. And then there is a bunch of kernel threads and a bunch of user threads. But again, the point is all of them are running in the same user space, right? What does it mean? It means that if you have a pointer arithmetic bug in your user code, that can totally crash your kernel. Why it's not a problem? Because the kernel does not multiplex between different processes. So speaking of which, a couple of things that OSV absolutely cannot do. So it is not a 100% replacement for Linux kernel for obvious reasons. So for example, forking is not allowed. Because again, the whole idea of forking is to basically create a copy of the address space and essentially start a process with this sort of existing copy of the address space, but started in a separate sort of address space so that the modifications that the child does, are not visible to the parent. So that is absolutely not allowed because we're still running in the same address space. We're running everything in there. So there's no process isolation. There is no sort of process isolation, not even just between processes, but between a process and a kernel. Again, your process can crash the kernel, which, by the way, means that the best things that are sort of OSV native are things that don't allow you to do memory manipulation from the user code. So things like Java or Go are actually a really good fit for OSV. You can still run your C and C++ applications, but like I said, anything that would result in a core dump in a traditional operating system would result in the whole image crashing here. Again, in this approach where you kind of sort of blast these droplets on the cloud platform, that is not a problem. Because in that approach, your container or your unikernel or the process running on the traditional Unix is basically doing one thing and one thing only. So in a way, a core dump is indistinguishable from the whole thing crashing because there is nothing else that is essentially running within the same sort of container operating system or whatever it is that you're running. And obviously, this has the least amount of drivers, because basically the only thing that it understands is essentially virtualized drivers, right? So the virt.io is the only driver that this unikernel understands. Again, not a problem with the anti-Kanti's approach, because his idea is, if you want a driver, it is available in the NetBSD's source code base. So once you're sort of linking the any kernel together, you can totally just lift a driver and start using it. It is actually pretty well suited for applications that are network intensive. It is not, that much sort of suited for the applications that are compute intensive, and for obvious reasons. Basically, if all you do is compute, any amount of virtualization will only hurt you. The real question is, why does it actually help with the network? So let me go through some of the points here. So in a traditional Linux kernel, two problems exist. First of all, the TCP/IP stack has to explicitly allow for multiplexing between different processes, essentially different clients on the system. Nothing like that is needed in the OSV's implementation because, again, remember, there is only one process and only one address space. Also, because they could implement it from scratch, what they did, they essentially took the idea that Van Jacobson sort of proposed as net channels. And I think it kind of sort of got rejected in its entirety by the Linux community because it would just require too much modifications of the Linux kernel. But the OSV guys could actually implement it. And what it does, it essentially allows them to run extremely quickly through the code that is typically part of the kernel, TCP/IP stack code. What it means is, and that actually was a surprising result of one of the profiling. What it means is that because the code path is so short, the data that arrived on your NIC doesn't actually leave the iCache by the time the application thread gets to see that data. So what typically happens in a traditional operating system kernel is that by the time the application sees the data has already sort of got evicted from iCache for all sorts of reasons, just because the code path is so long through the kernel, right? Here it doesn't happen, and that's one of the reasons that the IO-intensive applications are actually running much faster on OSV. So memory management is also interesting on OSV. So again, in a traditional sort of operating system, you basically have an OS image, and then you have different processes, and then you have sort of like something like JVM, sort of manipulating memory in its own right. Of course, in OSV, we don't have the other process, so the picture gets simplified. So we have just one process memory, which is actually indistinguishable from the OS memory, and we have something like JVM. But a trick that the OSV guys are pulling is actually kind of interesting. So they decided to flip the relationship between the operating system and the client code. So instead of trying to guess how much memory do you give to JVM, you give all of the memory to JVM, and then you essentially allocate a dummy opaque object that the operating system can use for its own needs. Why and how? Well, because it's all in the same address space. So basically, from the standpoint of the JVM, this is just a byte array that exists, and it has a reference that cannot really be garbage collected ever. From the operating system standpoint, it's a chunk of memory that it can use for its own needs. So basically, again, it completely flips the relationship between sort of how much memory is allocated to the application versus how much memory is allocated to the operating system kernel. Another thing that is actually pretty cool is because everything is running in ring 0, all of the CPU capabilities that are typically occupied by a real operating system kernel, like let's say MMU, are now available to the application code. What it allows them to do is, for example, it allows them to do optimizations on the garbage collection side. Because again, if you think about how garbage collection works in Java, it's basically, you have object 1, keeping a reference on object 2. Now, if that reference breaks, how could it possibly happen? Well, the pointer that was pointing from object 1 to object 2 got nullified. So that is a memory access. And if we have an MMU capability available to us in the application, we can actually track that memory access the same way that the operating system is tracking access for paging. So essentially, we can basically trap inside of an MMU based on the memory access, and thus essentially keep a bit vector of everything that ever got updated so that the garbage collector doesn't have to guess which object got updated and which ones didn't. So again, helps really sort of big time with garbage collection pauses. All of what I'm talking about is still very much a research, right? It's kind of like cool capabilities that are possible now. We haven't really sort of tried to run it, to the full possible extent. Essentially, kind of like just stressing them, right? But what's available and what is possible is kind of cool in its own right. So, by the way, how am I doing on time? Because I can. 5 minutes left. OK, awesome. So again, I apologize for speaking, really quickly, but I'm actually sort of kind of almost done, trying to impress you with OSV. So hopefully, I've done enough of it so that you guys at least check out the code base and check out the examples. The real question is, we actually seen it before. So I used to work for Sun Microsystems, way back when. Sort of, I didn't quite catch, the time when Java got invented, but I was reasonably close to it. And Sun actually had a number of projects where we tried to run Java on bare metal, right? We tried to actually come up with a CPU that would try to run Java. There was a company, still is, called Azul that is sort of trying to do that. And nothing really stuck, right? We don't really have Java native CPUs. Java is still very much sort of an application, software thing. So why should it work this time? I think, back when Sun was doing it, we actually didn't have a couple of things. So first of all, we actually didn't have, as well-developed hardware-assisted virtualization as we have today. And what I mean by that is all of the sort of CPU capabilities that Intel has pushed into the just, run-of-the-mill, Intel chips that are now available and essentially making I/O, especially, efficient in virtualized environments. We didn't have elastic infrastructure. Obviously, back then, something like cloud was not really, available. And to me, the ultimate sort of point that I think will make a difference this time is we didn't have something like a platform as a service component that would actually completely hide all of that complexity of how the application gets linked into an executable image away from the application developer. And we really need this piece of technology. And you know why? Because what I'm talking about is just this tiny portion inside of what a typical platform as a service, software component does, right? So all I'm talking about today is how this stuff gets linked and how it runs. But the platform as a service actually takes care of a lot of other developer needs. Routing, log collection, tracing, and all of the capabilities that essentially Brian took an issue with when he was talking about unikernels. Because his idea is that unikernels, if you view them as a replacement for traditional applications, are essentially completely unobservable and very difficult to debug. And I actually absolutely agree with that. If you're trying to just run it as a replacement to your traditional sort of application, lifecycle, it's not a particularly good idea. But if you're already embracing platform as a service, then you are giving up on those capabilities anyway. Because in a platform as a service, it's the platform itself that makes you observe the application, that makes you see the logs that are coming from the application. Because in a platform as a service, the application has been essentially sliced and diced in bits and pieces that only platform knows about. And you have to query the platform. There is no way you can SSH in one of those droplets that I was showing you. So in a way, if we're running platform as a service, then all of the unikernel capabilities can be used as optimization techniques for making our applications run faster. So with that, I will just spend 2 minutes essentially kind of sort of telling you about my pipe dream vision of a next generation data center. To me, it's basically a commodity rack provisioned hardware. I mean, that's kind of given. That's how most of the data centers are built today. Just enough OS, basically an operating system that runs on the hardware and is just a simple glorified device driver for all of the hardware that it needs to manage, plus a capability that gives me some kind of virtualization. Could be Xen, could be KVM, I don't care. So my operating system is something like CoreOS or SmartOS. That's sort of the Solaris equivalent of CoreOS. And just enough functionality to essentially boot this new next-generation format that I would like to call Docker++, because if you think about what Docker or sort of run C container really is, it's a different sort of executable format. And just like ELF was kind of a nice way to standardize all of the different executable formats on Unixes, we're now sort of having this format that can be used in all sorts of virtualized environments. And then, of course, on top of that, you actually have to have something like platform as a service. So Cloud Foundry is a good example, but there's a couple of other in the running. And that is, I think, the vision of a next-generation data center. And why does it matter? I think because if we go that way, then we can finally kill DevOps. Because the division of labor between the development and IT will be very clear. The development develops something that the platform can manage, and the IT basically racks and stacks and cables, and there's really nothing in between. Because the platform itself is capable of essentially giving such an incredible amount of observability into your application that you don't have to have a third team telling you how your application is behaving in production or in testing. Snowflakes in this type of a data center will not exist. Because again, the platform will not allow for a snowflake. You know how screwed up most of the Docker files are today? Developers don't actually have to deal with Docker files in this type of environment. So I hear that they're already clapping in the other room. So I guess with that, I will just open it up for questions. So thank you so much for listening.
Thank you so much, Roman. Do we have questions? All right.
Maybe I didn't hear about everything, but when you say you run the JVM and you have it was single core, everything, right? Or
no, it's actually capable of multi-core as well. So
all right, because that's what I went in with by the garbage collector, how it works, if it's not.
So this particular implementation is essentially a set of patches on top of OpenJDK that make it possible. Like it's a pretty involved set of patches. So you cannot really take with OSV. Because all you need is a shared object, you do have an option of taking libjvm.so from, let's say, an Oracle JDK. Like, that's totally an option, and you can do that. But then you won't be sort of experiencing all of these optimization techniques that I talked about. You would still, for example, get the benefit of a much shorter code path through the TCP/IP stack. So those guys did some measurements of Cassandra, and Cassandra benefits quite a bit, even on the stock Oracle JVM. But for the kind of optimizations that I was talking about, sort of the garbage collection and the memory ballooning, you actually have to get the OpenJDK with a set of patches.
Yeah, I meant more of when the garbage collection is running in multi-CPU mode.
Oh, in multi-CPU mode?
Like that, CMS or...
Right, that feature is actually available only on the single core. So again, in general, OSV is multi-core aware, but this particular feature is only on the single core. Yeah.
Thank you for the overview. I only see one issue if you can manipulate something running in ring 0 from the Java virtual machine, then everything is open, so you can manipulate every trap, every low-level thing from Java, and this is only allowing you running really friendly applications. You cannot run front code because otherwise you get a major security open door. So
again, I think we're having different frame of references, right? When you
if you are on ring 0, you can do everything. You can replace every trap in the operating system. So, and if you have memory manipulated from the Java virtual machine, which is a good issue for performance from the point of view of the Java virtual machine, you can manipulate anything on the. You can replace traps in the operating system, and this is only for your own code, not multi-tenant. Nothing. I would back nothing.
Again,
from
you're absolutely correct. If just random code is allowed into this image, but because how the platform is doing it, the platform is actually taking the source code, and everything else is done by the platform. So all of the bits, all of the binary bits that are essentially getting into the droplet are the binary bits that only platform can put into a droplet. Again, no more Docker files. Like, it's not a Docker file approach where a developer is trying to tell the system how to build the image. The only thing that developer is supplying is the source code for the application itself. And again, even like that source code can have bugs, sure, obviously. But if you're talking about sort of exploits, it is only if the developer puts those exploits in the code on purpose, then that becomes a problem. But that is a problem anyway. So if a developer is basically sort of putting exploits inside of a Docker container, you're in trouble anyway, because that Docker container can, open network connections that, would send, random traffic and do all sorts of, weird things, even though within the Docker container itself, I mean, there is nothing but the user code.
Thank you, Roman.
Thank you,
Ladies
guys.
and gentlemen, would you please give a round of applause to yourself, too, for helping Roman?
Yes, and thank you for helping me.
Chris and Thomas.